think we will start now, yes?
Yeah.
So, welcome everyone. It is my pleasure to announce a talk by Professor Feng-Yu Wang from Tiajin University. Professor Wang has been working for many years on problems in deterministic and stochastic differential equations and discovered many fundamental results for analysis important for diffusions on manifolds, for deterministic equations, and for stochastic differential equations on manifolds, and also on spectral gaps for diffusion generators. He authored also 3 books, if I'm right, about ergodic theory of Markov processes, but also on analysis on manifolds. And today the talk is about distribution-dependent stochastic differential equations. Please start.
Okay, thanks, Ben. Thanks for your introduction. Also, thanks to Danny for organization. So in this talk, I'd like to explain the main idea. How can one establish the exponential convergence in entropy, mainly in entropy, for nonlinear Fock-Polanyi equations? So this kind of nonlinear equation is characterized by the so-called McKean-Vlasov SDE in probability. So we also call it a distribution-dependent SDE. So now this contents. First, I will briefly explain the tool called log-sub inequality for the study of exponential convergence in entropy for microprocess. So this is a stochastic process corresponding to linear Fock-Polanyi equations. Then the question is, how can one manage for nonlinear PDEs? So it turns out we have to look at the so-called McKean-Vlasov SDE. So in that case, I like to also introduce some results derived by people like Venani, Li-Ming, and so on. So they looked at a typical model of nonlinear Fock-Polanyi equation called granular medial equations. For this model, they use particle system approximation to prove the exponential convergence in the so-called mean field entropy. It's not exactly relative entropy, but it comes from the mean field particle system. The idea is also comes from the classical situation that log-sub inequality gives exponential convergence for microprocess. So then the question is, how can one study the same thing for more general nonlinear Fock-Polanyi equation? For that case, maybe the lossing of mean field entropy no longer valid, or the tool log-sub inequality no longer holds. Okay. In particular, for degenerate situation, there is no any log-sub inequality. So then the main tool I will introduce is the so-called log-hierarchy inequality, which I introduced more than 10 years ago, also on manifold. So now we can do the same thing for nonlinear models corresponding to McKean-Vlasov SDE. So then I just, after introduce the main idea and the tools for the study, I just simply introduce main results we derived and also give specific examples. So this is the outline of the talk. So now the first part, convergence in entropy for microprocess. So in general, suppose we have a reference probability space. E here, B is algebra, mu is the probability. So then we look at a symmetric micro semigroup, PT, in the L2 space of mu. So there will be a duration form with, and also a generator. So this is standard framework in the theory of duration form. So then if we look at the initial distribution nu, which is absolute continuous with respect to mu, there's a density F here. So then at the time t, the distribution of the process denoted by PT star nu will be also absolutely continuous with respect to mu. The density is now PTF. PT is a semigroup. So then the relative entropy of the distribution PT star nu with respect to mu is nothing but the integral of PTF log PTF with respect to mu. So this standard definition. I denote this by capital H, PT star nu with respect to mu. As to look at the exponential decay of this entropy, so one uses the so-called bridging identity, which says if you look at the derivative of the relative entropy with respect to t, it's nothing but a minus Fisher information I sub mu of PT star nu. So by definition, for an probability nu with density F, the Fisher information is nothing but the duration form of F and log F. So this is only well defined if both functions are in the generalized domain of duration form. This thing is non-negative. So you can see the entropy is decay, okay? It's decreasing in time because the derivative is non-positive. So, under which condition this entropy decays exponentially fast, then we have the so-called H theorem. So giving a positive quantity lambda, so the entropy of PT star decays exponentially fast in lambda, in rate lambda, according to Bridging's identity. So this holds if and only if we have the following entropy information equality, which says if you look at the probability nu, the relative entropy with respect to mu bounded above by 1 over lambda times the information. So the proof is very simple, just straightforward. You take the derivative of the relative function according to Bridging's identities minus information. So if you have exponential decay, so this is equivalent to the derivative less than or equal to minus times entropy. So therefore, this inequality gives you information, entropy information equality. So the equivalence is more or less obvious. If we come to the diffusion setting, so say the duration form is local duration form, then the entropy information equality is equivalent to the so-called log-sub inequality. So for an function f in the domain of duration form with L2 norm equal to 1, so you look at the entropy. The entropy will be bounded about by 2 over lambda times duration form. This log-sub inequality was introduced by Gross in 1975 to study the so-called hypercontractivity of the semigroup. So, so far there are already many criteria on this kind of functional inequality. So for specific model, we have sufficient, even necessary conditions to see when this inequality holds. So therefore, for microprocess, we already have a lot of tools to study the exponential decay in entropy. So now comes to the Fock-Planck equation. If we denote by nu t, the PT star nu, which just means the distribution of microprocess at the time t, which is starting from the initial distribution nu. So then it's easy to see the nu t solves the following linear equation. The derivative of nu t according to t equals to a linear operator L star acting on nu t. So the solution of this equation is understood as the following integral type. So for n reference function f, for example, in the domain of the generator A, so the integral of f with respect to nu t is nothing but the initial quantity plus the integral from 0 to t. So now we use integration by parts. Now A of f, the integral with respect to nu s in ds. So this is just the definition of the solution of this linear equation. So log sub inequality is equivalent to the exponential decay of a solution to this equation in entropy, as I explained above. So now question is, what about non-linear Planck equation? So before moving on, I just introduce the study of a spatial model, so which called granular medial equation. So studied first by Carrillo, McKean-Vlasov in 2003, and also recently improved by these 4 people, so mainly Yiming Wu and his former students. So now I introduce the equation they started. So just look at the following equation for UT, the probability density function on RD. So the derivative in time of UT equals to Laplacian plus diverging in UT times the gradient of something, gradient of W plus V plus W cycle convolution with the density UT. So you see, if W is 0, so this is nothing but the yo-yo linear situation. So diffusion process will be generated by Laplacian plus minus gradient V. So this standard framework. So now we have a nonlinear term here, W cycle convolution of the density, because here before gradient we already have a density. So this gives you a nonlinear term. So now W and V are C2 functions. Also W is symmetric, which means Wxy equals Wyx. Then the cycle convolution is defined by the same thing with the probability measure, which is T dx. Then with convolution with the measure is nothing but just Wxy integral with respect to mu dy. So then again, if W is 0, we go back to the linear situation, and then the corresponding invariant probability will be nothing but e2 minus v dx. So this is normalization. So in this case, the exponential decay of the solution in entropy will equivalent to the log sub inequality, as I explained in general framework. So now the log sub inequality is for the measure mu sub v. So the entropy is bounded about by 2 over lambda times derivation 4. So if W is non-trivial, okay, so then they introduce the following mean field entropy. So first, they introduce the so-called energy function, so E VW of mu, giving a probability mu. So which is with respect again the reference measure mu sub v. So which is nothing but the relative entropy plus 1/2. Now the integral of W with respect to mu times mu, so product measure. So then this quantity could be minus because W could be negative. So then to make it non-negative, they take the mean field entropy as HVW to be the energy function minus the infimum of the function. So therefore this is non-negative. So in last situation, 0 point of this mu, there will be a unique 0 point of this mean field entropy. So that will be the unique invariant solution to the nonlinear Fock-Planck equation. So why they call this one mean field entropy? I will explain by using mean field particle systems. Now just assume W is weak enough such that E2 minus Vx minus Vy minus any positive lambda times W is integrable. So then for any n, capital N, we look at a particle systems of n many particles. So then the Hamiltonian will be given by H sub n, which is the summation of potential a V of x n point I, means the ith component. So this summation just gives you for each particle there is a potential. Then the second term is the interactions. So for fixed particles, the ith particle, so the interactions comes from other particles is given by the average. So this is what the mean field refers to. So this just average interaction. So then according to this function, we can define the so-called Gibbs measure, indeed the unique invariant measure for the particle system. So given by E2 minus the Hamiltonian, then dx. So here again, the integral is a normalization. So now according to these tables, for any initial probability on RD mu naught, we look at the product measure on the product space, n product of n meaning RD, right? So then look at the relative entropy with respect to the Gibbs measure. So then when the number of particles goes to infinity, this entropy, relative entropy, goes to exactly the mean field entropy introduced above. So this is why they call this quantity mean field entropy. This is indeed the relative entropy, limit of relative entropy for mean field particle systems. So now we look at the exponential convergence of the nonlinear equation, granular medial equation. To this end, we look at the particle system modeled by diffusion process on product space. So Xtn has n many components. So for the ith components, it goes like this E2 type SDE. We have a loess square root d bti. So square root refers to Laplacian operator. The minus a drift, which is gradient with respect to the ith component of Hamiltonian H capital N. So there is a dt here missed. Okay, there should be drift. There will be should be a dt here. So then here bti are IID, d-dimensional Brown emulsions, and we take initial values also IID with initial distribution mu 0. So there is a density rho naught here. Okay, so when Hessian V and Hessian W are bounded, which means we are looking at a nice situation that the drift is Lipschitz continuous. So then this result goes back to McKean, also summarized in a lecture loss by Schnitzman. If you look at the distribution of particle system, but only look at one particle, for example, the first one, the first component. So each component they have the same distribution because of the RD initial values. Okay. Then if you look at the distribution of one component at a time t, then you take a limit as n go to infinity, so it converges weakly to a probability, which is nothing but given by rho t dx. Rho t is the solution to the granular medial equation. So I denote this probability by mu sub t. Then in this paper by Villani and two other people, they prove that if you look at the distribution of the whole particle system, denoted by mu Tn, then look at the relative entropy of this one with respect to the Gibbs measure. When n go to infinity, so it converges to the mean field entropy of mu T. This mu T now is here, is on Rd, not on the product space. Convergence to the mean field entropy of mu T with respect to defined previously. So according to these facts, so it's easy to see the following result holds. This is the main result in the table. Let's say if the Hesse of V is uniformly positive, bounded below by a positive constant lambda, and if the Hesse of W is small enough, which is denoted by data, so uniform norm denoted by data, which is less than half lambda. So then they can claim the mu T, when T go to infinity, will convergence to a unique probability, U infinity. Moreover, the mean field entropy of mu T will decay exponential fast in the rate lambda minus 2 times theta. And now the proof is very simple. Firstly, according to the condition on Hesse V and Hesse W, we can apply Berkeley-Emery criterion for particle system to see the curvature of the particle system is bounded below by a positive constant, which is lambda minus 2 theta. So therefore, the log super inequality holds. The constant independent of n. So then according to the result in the linear situation, this log super inequality implies the exponential decay of the relative entropy for the particle system. Then according to the conclusion derived in this paper, so when n go to infinity, the left-hand side go to the mean field entropy of mu T, and this right-hand side here goes to the mean field entropy of the initial distribution mu naught. So therefore you have this exponential decay. So very clear argument. So now question is, moreover, I'd like to mention this paper by Li-Ming Wu and his former students. They use the Garninsky's condition on uniform log super inequality for single particle. So no matter how many particles in the system, but you just look at a single particle, but you fix the boundary condition as the state of other particles. You look at the single one, it is a macro process. Then if there is a log super inequality for such a process, which is uniformly in boundary condition also in the number n, and if moreover the interaction W is weak enough, so then there will be an exponential decay in entropy for the particle systems, and the rate is independent of capital N. So in this sense, they improve the conditions given by a paper by Villani and so on. Okay, so now the question we like to ask is, what can we do for the following general nonlinear Fock-Planck equation? So now the partial mu T equals to L sub mu T star mu T. So L now depends on mu. So given by the second order differential term Aij partial I partial j plus some drift Bi depends on both x and the distribution mu partial I. So which means if you look at SD, the drift term will depend on the distribution of the solution. And in particular, if A is just an identity matrix, then B is given by minus gradient of V plus W cycle convolution of mu, then this goes back to the granular medial equation. In general, such kind of even for the case independent of mu, classical case. So this kind of diffusion process may be even the invariant measure exists is no longer explicit. So there is some difficulty to establish noticeable inequality for corresponding invariant measure. Then in these things, if you go back to mean field particle systems, maybe it's non-trivial to define the so-called mean field entropy in these things. So therefore, we will use the classical relative entropy rather than the mean field entropy. And we will no longer use mean field particle approximation, but use some other tools. Okay, now in general, the SDE looks like this. We have drift term depends on the law, L sub x just means the distribution of x. Then noise term as usual. We denote A to be half sigma star. Then it's a positive definite matrix value function, okay? And denote mu sub t the distribution of xt. Then it's easy to see by E2 formula, just E2 formula to see mu t is a solution to the nonlinear Planck equation, just a solution to this 2.2 equation. On the other hand, by the so-called superposition principle, you can see this in a joint paper by Babu and Zuckler. And a weak condition like this, just integrability condition, okay? A solution to the nonlinear Planck equation also gives a weak solution of this McKean-Vlasov SDE. So therefore, there is a correspondence, one-to-one correspondence between distribution of solution to McKean-Vlasov SDE and the solution to the nonlinear Planck equation. So therefore, to study the exponential decay of solution to the nonlinear Planck equation, we only look at the same property for solution to the McKean-Vlasov equation here. So now I like to introduce the tool I will use in the study. The first one is called log hierarchy inequality, which was introduced in one of my papers 10 years ago. So there I consider diffusion of manifold. So generator is Laplacian plus gradient of some function v on a manifold. I proved that the following log hierarchy inequality is equivalent to the coverage condition. The coverage of the diffusion is bounded below by a constant k. And the log hierarchy inequality looks like this. If we look at the semigroup PT of log f at some point x, then by changing the order of log and PT, we can dominate this quantity by PT f at the point y. Then the area term given by the coverage lower bound and distance squared. So as an application of this log hierarchy inequality, we have the following entropy and cost inequality. The left-hand side is relative entropy of two the distributions of two solutions to the McKean-Vlasov SDE with two different initial distributions, mu and nu. Okay, so it can be bounded about by something, some constant times the L2W Wasserstein distance squared. So here the constants given by time t and also coverage lower bound. In particular, if coverage is positive, k is positive, so then the upper bound decay exponential fast. In this sense, you already have exponential decay entropy of the solution. But here W2 maybe you know, is nothing but the L2 Wasserstein distance defined for two probabilities on RD. So then to study the exponential decay of the distribution entropy, we also have to bound the W2 distance by entropy. So then if you bound W2 by entropy, then this exactly gives you exponential decay of the relative entropy, okay? So then the next, the second tool is so-called Talagrand inequality. So which was first found by Talagrand in 1996. It said that for the standard Gaussian measure mu on RD, the W2 distance square can be bound about by 2 times relative entropy. This is true for any new probability measures. This inequality was then extended to more general situation, for example, by Otto Vernani, also Babu, and Lidu. They said if you have log super inequality, so for some measure mu, you have this log super inequality, then the W2 distance square will be bounded about by entropy times C. So the same constant C. So then combine these two tools together, we can study the exponential decay of the distribution in relative entropy, but now just for the linear situation. Now in general, for the nonlinear situation, look at the McKean-Vlasov SDE. We again denote the distribution at the time t by pt star mu. So then we look at the operator pt of f, but now taking values in the space of probability measures at the point mu defined by f, the integral with respect to pt star mu, okay? So then what we need will be the following. We first need to show that pt star has a unique invariant probability measure. This can be proved by some other methods. I will not explain in details. I just simply assume this. Then we will need the log hierarchy inequality of the operator pt just for some t naught, okay? We have such a kind of log hierarchy inequality. Then the error term is given by the Wasserstein distance square up to some constant. Then we also need the Talagrand inequality for the unique invariant measure mu bar, okay? So put them together. So once we can prove the exponential decay in W2, then we can prove the same decay in entropy. So this is very clear. Moreover, we can prove that the sum of these two things can be bounded about by minus exponential times the minimum of these two things. Okay. So now, give an example. We look at the granular medial equation as I introduced above, but this now more general framework. We allow a non-constant coefficient A here. So it's a positive definite measure valued function A here. So just means in diffusion case, we have a non-constant diffusion coefficient. So of course, if A is identity, just go back to the model I introduced before. So now the thing is using the previous theorem. If we assume the mature valued function A is CB2 and is non-degenerate, bounded below by positive constant lambda, and V and W are C2 such that Hansen V is bounded below, not necessary to be positive, just bounded below by a constant, could be negative at this point. Then the Hansen of W is bounded as we assumed before. But for long distance, when the norm of X is large enough, So X and the gradient V should be bounded below by the square, the norm square, which means for long distance, gradient V gives positive, same direction of X, okay? But locally, V can be arbitrary. Then now the further condition is the interaction should be weak enough. You look at the Hessian of W, the uniform norm over 4 times the integral of this thing. So this B naught is a function on the half line, such that you have this kind of monotone condition. So remember, gradient V and gradient W cycle convolution is the drift, right? So now Z is free, just refer to the convolution. Then this inner product is bounded about by first the distance times some function of distance P naught. So this is some kind of monotone condition, but P naught is not necessary to be negative, could be positive, right? But we need this to be integrable. For example, if P naught is uniform negative for larger S, so this will be finite, right? So then we have a quantity R naught. So we need to assume this R naught is strictly less than 1, which means the interaction W should be weak enough. So then now we again recur the particle system here as already introduced before, the Gibbs major mu N here. And the point is, as I planned that we will use log super inequality for single particle was fixed boundary condition Z. For fixed Z, the state for other particles, you look at the behavior of one particle. So then the reference measure will be given by this conditional Gibbs measure. So it is now probability on RD, not on the product space. So therefore, the log super inequality, we have many ways to verify log super inequality. So now the result is assume H1 to H3, and also for each single particle and a fixed boundary condition, we have this log super inequality. Point is beta is independent of N. Then, according to the theorem I introduced above, we have this kind of exponential decay of entropy and also W2 was the rate, exponential rate. It's just lambda A is the lower bound of A of the matrix. Then beta times this guy, okay? So the remark is if A is identity matrix, then the condition is the same as those given in paper by Li-Ming Wu and his or others. So now the difference is we derived the exponential decay in relative entropy, not in the mean field entropy. In general, they are different quantities. So now, what about a more general situation? We look at now a more general case, and we assume that sigma is good enough, for example, CB2, and non-degenerate. The sigma star is invertible, and the inverse is bounded about by some quantity lambda. And we have this kind of monotone condition. This guy just comes from Ito formula of two solutions, distance square of two solutions, right? So then we will have a positive part comes from the distribution, and possibly a negative part comes from the inner product with the difference of space variables. So, and the condition of A, we can claim that PT star has a unique invariant probability measure mu bar, such as that PT star mu decays exponential fast in both W2 square and entropy, okay? So now the rate is K2 minus K1. So here we need to assume K2 is bigger than K1. The negative term is dominant leading term. And here we do not assume the symmetric property of W. So we can cover the granular medial equation with non-symmetric interactions. And finally, we can also look at the degenerate situation. Now look at the following SDE on the product space, RD1 plus RD2. And for the first component, XT, there is no any noise, just linear, some matrix B acting on YT. But in the second component, there is a noise, which comes from Brownian motion BT. And the drift contains both XT, YT, and also the distribution given by W again. W can be regarded as some interaction. So then we assume B is non-degenerate, just means B and B star is invertible. Then we can introduce a distance which is equivalent to the Euclidean distance, and also corresponding Wasserstein distance. So now the summation is the following. For fixed mu, look at grid in X of V, okay? So it is Lipschitz continuous in X and mu. So this is first assumption. The second is this constant theta 1, theta 2, the summation is strictly less than beta, such that this kind of inner product is bound below by minus distance square. So this condition is true if gradient W is Lipschitz continuous. It's easy to see. Because here theta 1, theta 2 could be positive. So if W gradient W is Lipschitz, then you can always find such kind of theta 1, theta 2. But we need the sum of them is less than beta. Beta is given in the model here. So then, according to our general result, we can establish both log-Halak inequality and also Talagrand inequality to show, and this condition PT star has a unique invariant probability, mu infinity. And for any initial distribution, PT star decays exponential fast in the rate 2 kappa, okay? With respect to both W2 square and also entropy. Here, kappa is given by quantities beta, theta 1, theta 2, given the condition C. I think maybe a little bit of time to introduce a degenerate example of degenerate granular medial equation like this. For an natural number M, you look at W in this product space, and then look at the following equation for probability density functions on R2M, okay? So now the derivative in time equals to Laplacian just in the second space variable Y, so it's degenerate now. Then the drift given by this linear term and interactions. Then according to the result, here is the cycle convolution we already introduced before. If theta here, theta okay, with theta. If there is theta small enough, such that as I mentioned, the gradient W is Lipschitz continuous with constant theta, then we can verify the condition C to see that PT star for this model will decay exponential fast in entropy and W2 square. Now the rate kappa is given here according to the theta Lipschitz condition here. I think time already over. I just stop. Thanks a lot for attendance. Thanks.
Thank you very much for a very interesting talk. We have time for some short questions. Are there any questions? Maybe I have a question. You introduced the stochastic differential equation, which is degenerate. Yes, you have two components. So you you know that there exists a density, yes, for this case, yes, for this two-dimensional system.
Yeah, this is it. Because in this case we have Hormeler condition. This is just by Hormeler theorem, there will be a density for this solution. So this comes from this condition. B star is invertible.
Ah, okay. Yeah.
Yeah, this last point.
So if you consider a particle system, you assume that Brownian motions are independent in this particle system, yes? For every equation, different Brownian motion.
Right.
Yeah. Can you have correlated, can you have common noise?
If you have common noise, this is a different type of models people are interested in also. If you look at the common noise, then this kind of result will be no longer true. This kind of result comes from the law of large numbers. So if you have RD noise, so somehow you are in the situation of classical law for large numbers. You can claim that the law of solution will convergence to the mean. So this is just a multi, just something like the mean of the solution. It was common noise is quite different, but you can, of course, you can look at maybe it refers to some different type of questions.
Okay, thank you. Are there any other questions? Okay, if not, we can close this session, and let me remind you that a message was sent about with another Zoom link to our coffee break, and everyone is welcome for a coffee break and to continue our chat and ask questions too. Thank you. Thank you very much.
Thank you.
Thank you, Professor Wang. Thank you, Ben.
Thank you.
Close the session and see you in the coffee break. Thank you.
Okay.